Hello, my name is Bella, and I'm a senior algorithm developer from Philips, and also the organizer of a machine learning meetup in Haifa. And today I'm going to talk about machine learning for predicting which kinds of algorithms to run in the medical imaging setting. Sorry. Okay, so just to give you some kind of a context, so whenever we do a scan, we get 2D images along the body. So those are kind of axial images that cross us. And usually what the physician, the radiologist, does is just scrolling over those 2D images and trying to find some kind of a problem. And of course, today, with the algorithmic capabilities, we can do much more. So we can create 3D information for the physician. We can create automatic measurements. We can make segmentations. And also, we can provide decision support for the physician to alert him to watch for something. So we can do much more. And what happens in reality that when you give to the physician such a software, they really rarely use it. So this is really a shame. We really, I guess everybody here really wants his physician, to use these kind of advanced visualization tools. The problem is that many of these algorithms are computationally expensive because they're operating in 3D. So idea here was, instead of making the physician wait for those algorithms, we now want for each case, whenever it gets to our software, we want to run the algorithm, the needed algorithm, and just prepare it for the physician. All right? So the idea here was to use a machine learning system that whenever we have a case, we want to predict which kind of preprocessing algorithm we want to run on this case. And actually, what happens with this data is usually we don't need to run anything, but there are some cases that we do need to do it. And what we are going to do is not to use the images themselves, but we have a lot of metadata that come with the scan. You can see here you have things like protocol name, study description, and actually much more tags that come with the scan. And we will use those to make this kind of prediction. Sorry. And you can see here from this data, we want to say, do we need any algorithmic execution? And if so, which kind? All right. So as I said before, we are using those textual features, so those textual tags. We want to create features out of them, so we will use a 2-gram bag of words model. And then we will take this feature representation and feed it to the machine learning classifier. And we found that random forest performed pretty well, so we chose this one. And we are actually, this thing is implemented also in the product, so we are using the MLE library from the Apache Spark general library. All right. Another question that we could ask when designing this is whether we want to use a dynamic model or offline model. And here the reality is that this kind of data, between different hospitals is, the variability of this data is very, very high because each hospital has different scanners. Of course, they have different languages, but really the data is very, very different. And it's very different to collect, data from many places in the world, create this offline model, and then deploy it. This is very challenging, and this is why we chose to go for the dynamic model. And also, another thing that is nice with the dynamic model is that now, if there are changes within the hospital, we can track them. We can retrain our model once in a while, and be much more adaptable to the hospital itself. So this is what we did. But it's good to remember that when you do such a thing, of course, there is a price to pay. It was much more complicated to deploy such a system. We are here talking about supervised machine learning. So now, for each scan, we need to create our labels on the fly within our software. So we need to implement this feedback loop inside the software. And also, of course, in terms of resources, it takes more time because we need to every once in a while to retrain this system on site. So those are kind of the trade-offs between the two. And how it looks like in reality, so whenever we get a scan, we don't know what to do with it. We still don't know if any algorithmic execution is needed for this scan, so we put it aside. And then after a while, if indeed somebody used this scan with any algorithm, now we create a ground truth for that, and we put it as a sample to the machine learning database. However, if after some period of time, let's say a week, nothing happened, nobody really needed to run anything on this scan, so now again we want to teach our supervised machine learning model that on this kind of data we don't need to run any algorithm. So this will again be brought to the machine learning engine with the label none, which means nothing needs to be applied. All right, and a little bit about the results. We had two data sets to test our method on. So the first data set, we had it manually labeled by clinical specialists because we didn't have those automatically inserted in our logs. So we needed somebody to actually label it for us. The second approach that we took in dataset 2 is actually to do it automatically, but those labels were noisy. But at least here we had these two datasets to look on and to get a feeling of what it will be like in deployment as close as possible. And here in the bottom you can see how the data looks like. So you can see that for most cases you have the label none, which means you don't need to run anything. So this is an unbalanced problem. Sorry, and it is a little bit challenging in this regard. All right. So some more some about the results. Here you can see a comparison. What happens if you just take the tags that you have in your metadata, or you extract some features from it, like we do with the 2-gram bag of words feature extraction. So here you can see that feature extraction on the right, in orange, you can see the feature extraction. And on the left, you can see without the feature extraction. And again, you indeed can see that there is a value to this feature extraction. And here's some more results. So we try to, because it's a dynamic model, and we try to see, all right, so what will happen in the field? How much samples do we need for this system to perform well? Because we have abundance of these non-samples, so because in many cases, in most of the cases, we don't need to run anything, we looked on how many positive samples do we need for the system to perform well. So here you can see that with 100 cases, we already reach sensitivity of 80%, which is pretty nice. This means that, in real life setting, this can perform pretty nice. All right, and to summarize it all, we saw that first we can use the machine learning to predict which kind of algorithm to run on the scan, and in such a way just to prepare the needed results for the physician, and of course help in the workflow in this way. Another thing that we talked about was adaptive learning versus offline learning, and we saw the benefits of adaptive learning, that it actually adapts to the data on the site and can be also retrained and track changes over time. But of course, we should remember that it costs more in deployment and also in resources. Oh, sorry. And maybe the final note is about data collection. So specifically here, we didn't have the ground truth labels. So you saw that we actually needed to construct 2 data sets to try to be as close as possible to the real world, to try to understand how our system will perform in deployment. And of course, one takeaway is just to try to put everything in the logs, and specifically, just to make you maybe understand better, our software, we deploy it once in a year. So if you don't put something in the logs, you don't have this information for a year, and you need to wait for it. All right, so there still are these kind of systems especially in the medical domain, and this is why it's very important. Sorry, thank you very much. You can contact me by mail, and you have a link to the paper, by the way, if you want more details. Thank you.